So let's now actually solve then for these pure states of LZ. Now, the equation that we're looking at, of course, is that LZ then applied to one of my angular functions, one of these, as we know they are called spherical harmonics, but we won't be assuming anything about them. When I apply that operator to my function, I have to get back some pure state value, LZ, so this is just a number, it's not the operator, acting on my function back again. Now, one thing that we can do to make our analysis a little bit easier is to try to go into something like natural units. If we look at the units on angular momentum, I'd like you to notice that angular momentum is units of radius times momentum, which would be units of meters, and momentum has units of kilogram meters per second, right? That's MV. So the final units on this are kilograms meters squared per second, and that actually is the same units as h bar. And that is a very nice fact. So let's define then this LZ number. Let's take care of our units. I'm going to call it some dimensionless parameter mu times h bar. So mu is dimensionless. And our job then is to solve for what this mu value is, and then we will know the LZ is just that mu times h bar. Notice we're not losing any generality here. We're just splitting up the LZ value into the part that has units and some other number. Our job is to find out that other number. Now, to find out that other number, let's look at the resulting equation. The operator LZ, we know from up above, is h bar on I times the derivative with respect to phi. That's acting on my function y, which depends on theta and phi. And that then must equal my constant times my state again. But my constant I'm measuring in units of h bar, so I'm going to call that mu h bar times y theta phi. And the first thing we notice is this is very nice. Our dimensional analysis was definitely a good idea because the h bars here will cancel out very nicely. And I'm left with a fairly simple equation. D by d phi of y of theta and phi gives me back I times mu times y of theta and phi. Now, I'd like to find out what the most general types of solutions allowable to this type of a system would be. And to do that, I want to solve this then without making any assumptions. So let's look carefully at the structure of our equation. One thing I'd like you to notice is, again, when I take d by d phi, I'm treating theta as constant. So we could just imagine theta here as having a certain constant value. And notice there's nothing really going on with theta on this side of the equation either, right? Theta is really just a label. So sort of in the backwards way of the argument I had given up above, what we could do is for each value of theta, I can just cover up theta, and then I have an equation that I need to solve, right? And then I can change the value of theta and resolve this equation at the next value of theta, and so forth, and thereby build up my entire solution. The key observation is that at this stage in the analysis, I can suppress the fact that these things depend upon theta and just solve the phi part of the equation, knowing that at the end of the day, I simply have to reassemble all of my solutions. So what I'm going to do is I'm going to X these out here in dashed lines, right? And I'm going to just suppress thinking about this. Suppress this dependence for now. So then when I do that, the resulting equation is d by d phi of y on phi. Gives me back just I mu y on phi. And what's nice about this is that now, because I'm suppressed thinking about the thetas, I know I have to put them back in later, my y, what's really important actually is how it depends on phi. That's what's determining the behavior of this overall equation. And because that behavior depends only on phi, this partial derivative I can now rewrite as a total derivative. This is dy d phi. And now I have an ordinary differential equation to solve. And we can solve that in the usual way using the ordinary differential equation version of separation of variables. We move all of the y's to one side of the equation. I can do that by dividing both sides by y. And we put all of the theta dependencies on the other side of the equation, phi dependencies, and we can do that by multiplying through by d phi. And then I have a result that I can integrate on both sides. And we can perform the integration pretty handily. This would just be the logarithm of y would equal I mu times the variable phi. But now there's also always plus a constant. Now here's where we have to be a little bit careful. In fact, let me write this out a little more carefully. I'm going to call this log of y. I'm leaving a little bit of space here. And this y depends upon phi, right? I'm leaving a little space here because those thetas are going to come back in just a moment. Now, I'm solving this equation separately for each value of theta, and the idea then is to reassemble the solutions at the end. Now, when I perform this integration for a particular value of theta, this is just some arbitrary integration constant. There is no guarantee that I get the same constant every time I do this integration. The other pieces, of course, are just my integrals. Those will be fixed. But this c may depend on my particular value of theta. And if I want to reassemble the full y theta phi function, I should, as I include the dependence on theta in c, I should also remember that I'm actually describing the full function y. Now at this point we can solve for y of theta and phi by exponentiating both sides. So this will be e to the c, c will depend on theta, times e to the I mu phi. And now c is just some arbitrary function of theta. And so when I exponentiate it, I just get another arbitrary function of theta. So I can write this as a function that depends only on theta. And then I have the angular portions e to the I mu phi. That tells me then the behavior of my solution. Now, here's where also our physical model is going to help our thinking. This tells me, notice what I'm getting here is a set of states where mu at first appearance can have any possible value, right? Nothing here is telling me what the value of mu has to be. So this would seem to indicate I have a continuous set of solutions for these y's available to me. But that can't be right because we know we are bound into a finite space. And being bound into a finite space, here's my effective problem, right? I know I should expect discrete solutions that reflect the fact that I am in this finite space. And you can see how this works, for instance, on the phi variable, right? Phi is telling me how far around, it's telling me what's known as my longitude, right? Theta is telling me my latitude as I'm coming down, off of the North Pole, but phi is telling me as I go around a full circle, I come back to myself, right? And those phi values are telling me my different longitudes. Now, a physical wave function on this sphere, right, must be a continuous function, right? It must have the same value if I start for small positive values of phi, which would be here, right? That would be along the Greenwich Mean Time, right, if you will, right? That's my first point of longitude. And now as I go around the globe like so, and I come back, and phi varies from 0, by the time it takes on the value 2 pi, I'm looking at the neighboring point. And if my solutions are physical, they must be continuous functions. I have to have the same value, whether or not phi is 0 or phi is 2 pi. That is my boundary condition. So my boundary condition has to be continuity of y, right, at theta equals 0 and phi equals 0 and phi equals 2 pi. These represent the same exact point in space. So I know y at theta comma 0 has to equal y at theta comma 2 pi. But y at theta comma 0 from my solution here would be f at theta times e to the I mu times 0. And that, of course, we know is 1. And on the right-hand side, what I have is f of theta times e to the I mu times 2 pi. Now I have a condition on mu. The f's cancel out nicely also, so this must equal 1. And I can ask, well, e to what power, right? I times some number gives me 1, but we know that these are just points on the unit circle, right? And they go around as I increase mu, the unit circle. And I'm just asking for each time at which I will hit the x-axis on my unit circle. And that, of course, will happen when 2 pi times mu is equal to, well, it could be 0, right? I would be on the axis. Or it could be 1 full trip around, right? So that could happen at 2 pi, or 2 times 2 pi, etc. All possible integers times 2 pi, and certainly minus 2 pi I would take me backwards around my circle, would still land me on the real number 1. So this is my unit circle, real and imaginary components. So in fact, these can be all plus or minuses. And we conclude, therefore, that mu must equal 0 plus or minus 1 plus or minus 2, etc., simply by dividing both sides by 2 pi, which is just another way of saying that mu has to equal some integer. So I will call that integer m, where m is a member of the integers. Beautiful. So we now have learned a number of important facts. We've learned, firstly, that the allowed values of LZ are, in fact, m, right? But remember, the LZ values are, we call them our allowed mu's times h bar. H bar carries the units. So it's m times h bar, where m, as we've just said, has to be a member of the integers, right? It could be anywhere from minus infinity down to minus 1, 0, 1, and so forth. And we also learned that these functions that depend on theta and phi, right, are going to be some function of theta times e to the I m phi. Now, these y's, right, we can characterize them then by their LZ values, and their LZ value is characterized by this integer m, so this is usually written as y sub m. And this function we have to be a little bit careful about. It could depend upon m, and it may depend on other things, right? We've only so far looked at LZ. We have to remember there are other possible dependencies that may come in as I look at L squared. I'm ultimately seeking functions of y that are going to somehow be related to the eigenvalues of L squared, so there will be some additional labeling that we will have to add to this a little bit later on. But at this point, I think we've got a nice complete solution for LZ.